The first radio maps didn't show a point. They showed something wider, softer, a faint, extended glow encircling the position of 3 Atlas. The third confirmed interstellar visitor to pass through our solar system. Not a sharp dot like a distant quasar or a compact radio source, but something diffuse, spread out, halo-like. That alone triggers caution. Distance, telescope beam shape, and background contamination can all fake structure in radio images. Faint extended emission is exactly the kind of signal that calibration errors, side lobes from bright nearby sources, or imperfect background subtraction can manufacture out of noise. Yet as the analysis deepened, as independent reductions were run, and the glow was tracked across multiple observation epochs, a pattern emerged. The emission seemed to follow the object's predicted position. Not perfectly. Not with the clarity of a textbook detection. But persistently, night after night, moving through the sky in a way that background galaxies and instrumental ghosts do not. The tension among observers wasn't "we found aliens." It was something quieter and more unsettling. We found something that behaves like a physical envelope around a moving object, but the usual explanations don't fit cleanly. This is the kind of detection that forces a hard question onto the table before celebration is allowed. Is this real emission from a region surrounding the interstellar visitor? Or is it a mirage? An artifact born from the way radio interferometers reconstruct images from sparse data? Because radio telescopes do not take pictures the way optical instruments do. They sample the sky with arrays of antennas, measuring correlations between signals, and then mathematically invert those measurements into images. That inversion is never perfect. It inherits assumptions about what the sky should look like, and when those assumptions are wrong, the resulting map can contain ghosts, faint structures that look real but are actually the telescope's attempt to fill in missing information. A weak extended glow around a faint moving target sits at exactly the boundary where such artifacts thrive. So before the glow can be treated as astrophysics, it has to survive an audit. It has to endure attempts to destroy it through different data weighting schemes, alternate calibration strategies, and independent reductions by separate teams. The central suspense is methodological. If this is real, it must persist when you try to make it disappear. The tests began. The radio data were reprocessed with different imaging algorithms, changing how the interferometer's incomplete sampling of spatial frequencies was handled, adjusting how bright sources in the field were subtracted, varying the assumptions about Basel-independent phase errors. Faint extended structures are fragile under such manipulations. Over-aggressive cleaning can erase them. Too gentle cleaning can leave residuals that mimic real signal. The balance is delicate, and the outcome is never guaranteed. But across multiple reductions, using different weighting strategies and different background models, the glow remained. Not identical in every map, not with the same brightness or exact morphology, but present in a way that suggested it was tied to the sky position of 3I Atlas, rather than to the reconstruction process itself. That reproducibility, even approximate, shifts the burden of proof. The glow survives skepticism. It exists in the data coherently enough that dismissing it as pure artifact becomes harder than accepting it as a detection requiring explanation. If you enjoy this unfolding mystery, subscribe for more Beyond the Solar Veil cosmic documentaries. Motion becomes the key forensic tool. A background galaxy, no matter how faint or extended, remains fixed to celestial coordinates. It doesn't drift. It doesn't move relative to the stars. But the Atlas does. It travels along a hyperbolic trajectory at tens of kilometers per second relative to the Sun. And that motion translates into predictable shifts in right ascension and declination over days and weeks. So the most revealing test is whether the radio glow follows the object's ephemeris, not perfectly, because the emission region could have spatial extent and internal structure, but systematically in a way that tracks the predicted path. If the glow stays centered on a fixed sky position while the object moves away, it's background contamination. If it drifts with the object, maintaining approximate alignment across observing epochs separated by days, then it's associated with the visitor. The analysis showed drift. Not sharp, point-like tracking, but a coherent displacement consistent with the object's motion through the solar system. The glow appears to travel, and that traveling behavior cannot be easily explained by instrumental effects or static sky sources. But motion alone doesn't define the phenomena. The morphology matters, how the emission is distributed spatially, whether it's symmetric or lopsided, whether it shows directional structure or remains isotropic. Does the glow stay centered on the nucleus, or does it lag behind like a weight? Does it stretch along a particular direction, perhaps aligned with the solar wind, or the object's velocity vector, or the interplanetary magnetic field? Subtle asymmetries in the brightness distribution, offsets in the emission centroid, or changes in the apparent angular size across epochs all encode information about the physical processes generating the radio signal. A symmetric shell suggests an isotropic environment or a steady outflow. A trailing extension implies interaction with a flowing medium. A lopsided distribution could indicate a bow shock, a fragmented coma, or an asymmetric release of material. Early maps hint at structure, some elongation, a possible offset from the predicted nucleus position. But the signal-to-noise is low, and the morphology is not yet definitive. The glow behaves like something responding to motion, interacting with the space it moves through, but the details remain frustratingly ambiguous. Here, the investigation confronts its most destabilizing piece of evidence: silence and other wavelengths. If the radio glow arises from a large, dusty coma, grains scattering sunlight and emitting thermally, you would expect to see it elsewhere. Visible wavelength imaging should detect scattered light. Infrared observations should pick up thermal emission from warm dust heated by the sun. Millimeter wave measurements should bridge the gap between radio and infrared, revealing the cold outer envelope of any extended dusty structure. But those companions are weak, absent, or inconsistent. Optical photometry shows at best a faint, compact coma, nothing that matches the spatial extent implied by the radio glow. Infrared upper limits constrain the total dust mass and temperature, and those constraints don't easily accommodate a halo large and dense enough to explain strong radio continuum emission through thermal processes alone. Millimeter observations, when available, show marginal or non-detections, failing to confirm the bridge expected between radio and infrared if dust were the dominant contributor. Absence becomes data. Non-detections are not failures, they are constraints. They narrow the parameter space, eliminating interpretations that predict signals we should have seen but didn't. If a radio halo exists without a corresponding visible coma, the emission mechanism is not simple dust scattering. If it exists without strong infrared thermal counterparts, the dust density or temperature distribution must be unusual, or dust isn't the primary emitter. If gas-driven activity were responsible, molecular emission lines, ionized plasma, active sublimation, certain spectroscopic features should appear at specific wavelengths tied to molecular transitions or recombination processes. But narrowband searches for emission lines in the radio and submillimeter regimes have yielded only upper limits or tentative detections too weak to definitively confirm widespread gas activity. The viewer should feel the squeeze. The glow exists in one observational channel, radio continuum, and that isolation makes interpretation harder, not easier. It's an outlier, and outliers demand extraordinary explanations or extraordinary skepticism. The most plausible physical framework shifts focus from the object itself to the space it moves through. At interplanetary distances, 3I Atlas is several astronomical units from the Sun, well within the heliosphere. Space is not empty. It's a flowing plasma. The solar wind, streaming outward at hundreds of kilometers per second, threaded with magnetic fields, carrying energy and particles that interact with any obstacle in their path. A fast-moving object, even a small, inactive one, can disturb that flow. It can create a bow shock ahead of itself, where the supersonic solar wind slows and heats. It can leave a wake behind, where the plasma reestablishes equilibrium. And in those disturbed regions, particles can be accelerated. Electrons can gain energy from magnetic reconnection, shock acceleration, or turbulent processes, and energized electron spiraling in magnetic fields produce synchrotron radiation, radio emission generated not by thermal processes, but by relativistic particles gyrating in field lines. Synchrotron emission is common in high-energy, astrophysical environments. Supernova remnants, active galactic nuclei, pulsar wind, nebulae. But it can also occur on much smaller scales, in the local heliosphere, wherever conditions exist to accelerate particles. The key requirements are magnetic fields and a population of relativistic electrons. The interplanetary magnetic field provides the former. Solar wind interactions, shock structures, or reconnection events could provide the latter. If 3I Atlas is generating a bow shock, or disturbing the solar wind in a way that energizes electrons, those electrons could radiate at radio frequencies, producing a diffuse glow around the object without requiring large amounts of dust or gas. The emission would be faint, extended, and potentially variable depending on solar wind conditions and the object's velocity relative to the plasma flow. Morphologically, it might appear lopsided or asymmetric, with brightness concentrated on the upstream side where the shock forms, and a trailing wake downstream. That spatial structure, if detected clearly, would be a strong indicator of plasma interaction rather than thermal dust emission. But synchrotron emission comes with testable predictions. It produces a specific spectral shape, a power law distribution of radio flux versus frequency, that differs from thermal emission's characteristic curve. It is often polarized, because the magnetic field organizes the emitting electrons and their radiation carries that directional information. And it can vary in brightness on short timescales if the solar wind conditions change, or if the object's velocity fluctuates due to non-gravitational forces. Checking for these signatures requires multi-frequency radio observations to measure the spectral index, polarimetry to test for linear or circular polarization, and repeat campaigns to search for variability. The existing data, limited to a few observing epochs and narrow frequency coverage, do not yet provide definitive answers on all these fronts. The spectral information is sparse. Polarization has not been measured conclusively. Variability, if present, is subtle and could be confused with changing background contamination or evolving data quality. The hypothesis fits, but it is not yet proven. There is also a complication that cannot be ignored: Jupiter. Depending on the timing of observations and the sky position of 3A Atlas, the object may have been projected near Jupiter on the sky, or even physically close to Jupiter's orbital region during some observing windows. Jupiter is one of the brightest radio sources in the solar system, emitting strongly at meter and decimeter wavelength through synchrotron radiation generated in its powerful magnetosphere. That emission is extended, variable, and difficult to model perfectly in interferometric data. Bright sources haunt radio maps through side lobes, artifacts in the image caused by incomplete sampling of spatial frequencies, and imperfect subtraction of Jupiter's signal could easily create false extended structures near any faint target observed in the same field. If the radio glow around 3I Atlas appeared when the object was close to Jupiter in projection, the detection becomes treacherous. It could be real. It could be contamination. Or, more subtly, it could be both. Jupiter's magnetic influence extends far beyond its visible disk, and particles accelerated in its magnetosphere can populate a large volume of space, creating a radio-loud environment that might genuinely enhance or interact with structures around nearby objects. This ambiguity is not a flaw in the investigation. It's a fork in the road. Jupiter's presence either collapses the case, proving the glow is an instrumental or background artifact, or it sharpens the case by providing a plausible physical context. If 3I Atlas passed through or near Jupiter's magnetospheric domain, the interaction could energize particles around the visitor, amplifying radio emission that would otherwise be too faint to detect. That interaction would still be real astrophysics, even if Jupiter's environment provided the necessary conditions. Distinguishing between these scenarios requires careful astrometry to determine the exact geometry, detailed modeling of Jupiter's radio emission, and its side lobes in the interferometric data, and ideally observations of 3 Atlas at times when it was west, far from Jupiter, to test whether the glow persists or disappears. Those tests are ongoing or planned, and the results will either eliminate Jupiter as a confounder or force a reconsideration of what around 3E Atlas actually means. The investigation now sits at a three-way intersection, each path leading to a different class of explanation, each demanding different follow-up observations to confirm or rule out. The first mechanism is thermal dust emission, a broad, cold halo of dust grains, possibly from recent outgassing or fragmentation, producing faint radio continuum through thermal radiation. This predicts companions at infrared and millimeter wavelengths, and the absence or weakness of those companions constrains the dust mass, temperature, and grain size distribution to narrow, perhaps implausible ranges. The second mechanism is synchrotron radiation, relativistic electrons accelerated in shock structures or plasma turbulence radiating in the interplanetary magnetic field. This predicts polarization, a non-thermal spectral index, and possible variability, none of which have been definitively confirmed or ruled out yet. The third mechanism involves coherent plasma processes, bursts, instabilities, or resonances that can generate radio emission under special conditions, often frequency-specific and time-variable. Such processes are known from solar radio bursts and planetary magnetospheres, but applying them to a small interstellar object requires conditions that may or may not exist. None of these mechanisms can be declared the winner with the data in hand. Each fits part of the evidence. Each struggles with other parts. What the observations demand next is clear. Broader frequency coverage to measure the radio spectrum precisely, polarimetry to test for a magnetic field alignment, repeated observations under different solar wind conditions, and geometric configurations, and careful cross-wavelength campaigns to search for faint infrared, optical, or spectroscopic counterparts that might have been missed in earlier surveys. The mystery has not been solved. It has been given shape, an investigable shape, with testable predictions and paths forward. And that transformation, from "we found something strange" to "here are the three things it could be, and here's how we distinguish them," is how science progresses when certainty is not yet available. Looking forward, the observational window for 3E Atlas is closing. As the object continues outbound on its hyperbolic trajectory, it will dim at all wavelengths, and the radio glow, if it was ever detectable above noise, will fade further. Future observations will require longer integration times, larger telescopes, and more favorable geometric alignments. The Very Large Array, the Atacama Large Millimeter, Submillimeter Array, and next-generation facilities like the Square Kilometer Array will eventually provide the sensitivity and resolution needed to detect and characterize faint radio structures around small bodies at large distances. The Vera C. Rubin Observatory's optical surveys will catch future interstellar visitors earlier, providing better context for coordinated radio follow-up. The James Webb Space Telescope's infrared capabilities might detect thermal signatures that current instruments miss, constraining dust properties and ruling in or out mechanisms that rely on extended coma. But for 3A Atlas specifically, the data we collect now may be all we ever have. The glow, if real, is a transient phenomenon tied to a specific moment in the object's journey, a moment that is already passing. What remains is not an answer, but a better question. A radio glow, if confirmed as real emission rather than artifact, would mean 3I Atlas is not just a solitary traveler, not just a dark nucleus coasting through the void. It would be an interaction, a moving boundary layer between an object and the living medium of interplanetary space. It would be a site where plasma flows, magnetic fields, and perhaps remnant outgassing or fragmented debris conspire to generate signals we can barely detect. And if the glow is not real, if it collapses under further scrutiny into instrumental noise or background contamination, the story is still meaningful. It exposes the epistemic edge where modern astronomy can mistake its own reconstructions for nature, where the mathematics of imaging can create structures that look physical but are not. It shows how carefully science must tread when signals are faint, when the data are sparse, and when the desire to find something new must be tempered by the discipline to test every alternative explanation first. A radio glow around an interstellar object would be extraordinary. But extraordinary claims require extraordinary evidence, and the evidence for now remains provisional. The emission is faint enough that confirmation bias could shape interpretation. The morphology is ambiguous enough that multiple physical models remain viable. The cross-wavelength silence is strong enough that simple explanations struggle. And the presence of Jupiter in the observational context is significant enough that contamination cannot be dismissed. What we are left with is a signal that survives preliminary audits but not yet definitive proof, a pattern that looks like motion-correlated emission but could still be a sophisticated mirage, and a set of competing hypotheses that cannot yet be ranked with confidence. The investigation continues not because the answer is clear, but because the question has sharpened into something testable, falsifiable, and worth pursuing. In the end, the faintest signals often force the greatest discipline. They sit at the boundary of what instruments can measure, where noise and signal blur, where assumptions about calibration and data processing can tip interpretation one way or another. The radio glow around 3I Atlas, whether real or illusory, is a reminder that the universe is vast, our tools are imperfect, and certainty is earned slowly, through repeated measurements, independent confirmation, and the patient elimination of patient elimination alternatives. It is a reminder that astronomy is not just about discovering new objects, but about understanding the space they move through, the plasma, the fields, the radiation, the environment that shapes what we see and how we see it. And it is a reminder that mystery, in science, is not failure. It is the edge where knowledge meets the unknown, where data meets interpretation, and where the next observation, the next instrument, the next theoretical insight might finally tip the balance toward understanding. The glow may be real. It may be artifact. But the question it forces us to ask, what does it mean to see something that exists only as reconstructed mathematics until we believe the map, is worth asking and worth pursuing, even if the answer remains just out of reach.